So hello everybody, thank you for coming. May I introduce to you Andrés Santos from University of Extremadura in Spain, in Badajoz. This is the correct pronunciation. I have practiced many times this name. This is the name of the city.
Your Spanish is better than your English.
Thank you very much. I will continue in Spanish. Okay, so he's a scientific visitor here, visit our group. We have a common project. Also, one of his students, Ana Montero, is here, and we have some common scientific work. But no, certainly here in the pub, he will speak about some more common and more easy science, which is the title is can be seen here, challenging intuition. So he will speak something which is not so straightforward to understand. At the first sight, it is surprising, but you know, everything can be understood. This will be, I think, the conclusion finally. So I give the to you.
The word. Okay, thank you. Thank you, Peter, for the introduction. I am very happy to be here in Veszprém, and especially in this so kind atmosphere. Well, as Peter said, the title is Challenging Intuition, and then I will illustrate that with two examples, which are more or less related to probability, mathematical probability, but without practically no equations at all. And first of all, Peter pronounced Badajoz quite well, but maybe you wonder where Badajoz is located in Spain. So here we are here right now. So Badajoz is there. This is the province of Extremadura, and we are sitting just on the border with Portugal. Okay, so it's a small city, relatively speaking. And according to Google Maps, it takes more than 600 hours to go by walking from here to there. So you will need to be prepared for that. Okay, so we go back to the main topic, intuition. Well, intuition, of course, is very, very important in science. No? When you are investigating something, you need a guide to orient where to look for something that you think is interesting. So you must base that on intuition. That has happened along history. For instance, well, Newton, when he discovered his universal law of gravity, according to legend, he was challenged by the fact that the same force that makes an apple fall is the same force that actually makes moon go around the Earth, or the Earth around the Sun. So there is something universal there. So it's not obvious, but you are clever enough, you are a genius, maybe your intuition can help you that. Another example maybe is Darwin with the theory of evolution. Also, he needed a lot of intuition. He was observing the same world as many other people before, but he had this kind of intuition to think that the evolution was working to make different species change along time, no? Along geological times. Well, Mendeleyev's periodic table is another example, and also Einstein's discovery of the special relativity. It seems that when he was a teenager, at that time he didn't have a mustache, but otherwise you wouldn't recognize him. So he imagined what would happen if he was sitting on a light beam, how everything would look like in that frame of reference. And this question is what led him to the discovery of Einstein's the special theory of relativity and then the general relativity. Okay, so intuition is very important, but sometimes our common sense intuition, the one that is fed from our everyday experience, maybe could be misleading. I'll give you only two examples. I can imagine that for a primitive man, he was wandering around, and for him, well, the Earth, the place I live, must be flat. Why not? There is no more information to imagine that this is not the case. Of course, by observing the stars and planets, and also how the ships sail on the sea, people realize that the Earth is actually not flat. Nowadays, still there are people who think the Earth is like that. Also, more recently, in 19th century, people couldn't believe that an object heavier than air, without flapping the wings like a bird, could fly. Here you have a plane made of bricks to translate the idea of something very, very, very heavy. So it's impossible for it to fly. Of course, maybe not if it is made of brick, but we know that we can fly. So that means that in science, intuition is not something that comes from nowhere, it's trained. We change our intuition as we are learning more and more, so it's something that must be trained or educated, and this, at least for me, happens every time. I discuss with Anna, who is my PhD student, about what we are doing, and I have an intuitive explanation of something, but the result gives a different answer, and then you revise your intuition until understanding that you were wrong, and you have to change that. And next time, you have learned at least this. Okay, so I'm going to illustrate that with two examples. One is the so-called Newcomb-Benford law. Many of you maybe already know that. If not, okay, I will try to explain that a little bit. Okay, to do that, imagine I have a long list of something, for instance, of population cities. This is a table drawn from Wikipedia. Here there are maybe 60 or 80 cities. Imagine I have a long list, maybe 1,000 or whatever. And I have here the population of the different cities. Here they are ordered from more populated to less populated, but that doesn't matter at all. I mean, the order is completely not important here. What we do is to focus on the first digit. So you have here 3, 2, 2, because they are ordered. There is no 4 at the level of 40 million people. But maybe in the long list you will find 400,000 or 40,000 or just 400. So 4 will be represented in the long list. So we focus on just on the first digit. Okay, we take a long list of population, but we can take practically any other list. For instance, we can take, also this is from Wikipedia, a list of lakes. In each case, we know from this table the area, the length, the maximum depth, the volume, so many data associated with that. Even in that case, according to Wikipedia, these data are given in different units in the international system of units. Here you have square kilometers. These are kilometers, meters, cubic kilometers, or square miles, miles, feet, cubic miles, which is, as you know, it's the preferred unit by Anglo-Saxon countries like United Kingdom and United States of America. Here you have the conversions, how to go from feet to meter, from mile to kilometers, and so on and so on and so on. This is more or less the conversion factor. And again, we focus on the first digit. These are the ones that are, okay, indicated here. I can take both in one system of units, in other system of units, only one system, only the other system. I can shuffle all of them in any order as before. And also I can obtain data. You can imagine, for instance, the lengths of rivers, height of mountains, or maybe I can ask, go to a lab, or someone doing molecular simulation and ask that person, please give me a list of numbers you obtain when crunching, doing the simulation, have a lot of numbers, and in the end, give me the list. So I focus only on the first digit. The first digit can be from 1 to 9, so there are 9 possibilities, not 0, because of course 0 doesn't give you any information, and the digital position doesn't matter. I mean, if you have a decimal position here or there, well, you can forget about that. So you can multiply by a power of 10 or divide by a power of 10 in order to move that decimal position. In any case, 0 is not included. So there are 9 possibilities. Imagine you have very long list of numbers from different sources, and the question I want to ask you is, approximately, on average, what is the expected frequency of 1s, of 2s, of 3s, and so on? Okay? So I'll give you 5 possibilities. Maybe could be something similar to that. I created that. They are not taken from real data, none of the graphs, so I created more or less. It could be something like that, meaning that approximately is uniform. So you have approximately 1/9 of the numbers begin with 1, 1/9 begin with 2, and so on. This is possibility A, or maybe you have something like that. So 1 appears more frequently, then 2, and then it is decaying. Here 9, maybe by accident, is partly equal, or maybe somewhat larger or smaller than 8. But the tendency is to decay, or just the opposite. It grows. This is the third possibility. A fourth possibility, having this kind of non-monotonic behavior with a minimum in the middle and local maxima in the ends, or just the opposite. Okay? So please think which one is correct, the other 4 are not correct. Please think of which one of these 5 you think is the correct one. Okay? Now, you have a question or? Okay, no, don't tell me. Because, well, you can tell me if you don't have here a smartphone so that you can go to this QR and then make the selection. I'm sorry, Xavi. What is Xavi? Xavi. I'm sorry. I know you don't have a smartphone. But I myself, I'm going to do it. Maybe I must be, because I want to make sure that. Any problem with those of you who tried? So you can, if you have something like that on your mobile phone, then you can already make the selection. And then this Sunday we'll have a European election. So this is not the same, because in that case only one is correct. Okay, so if everyone had the opportunity to mark their opinion, let's see what we have. It should appear here. Ah, you cannot see that. I don't know why you cannot see that. In any case, I'm going to. I have to close this, maybe. Well, technical problems. Yeah, but I lost my connection. There is no signal. I don't know why. I do that in my classes, it works, so I can go. Let me. No ampliar, duplicado.
You can see it. Thank you very much.
That's the weight of your personality.
Only 7 people participated in that. Except me. I'm going to participate. I indicate my vote, okay? And I had the advantage that I know the answer. So the truth is what I'm going to indicate now. Anything to remember is, so it hasn't changed? Now. So the correct one is B. We are going to see which one was B. You remember, B was the one in which ones appear more frequently and then it decayed. So I have to recover. So this is when I was asked that about maybe 20 years ago. The guy who taught me first about this was Parrondo, who is the one I will talk in the second part. By coincidence, he's a good friend of mine, so he's younger than I am. And he told me, because he likes very much popularization and this kind of curiosities, and he said, well, 1, 2, all of them are equivalent. The answer is this one. And why? Because the trick is that I insisted that you can use, in the case of the lakes, any kind of units. So the law shouldn't depend whether you are using the international system, the Anglo-Saxon system, your own system. You can define your own unit length. Possibly in Hungary there are medieval units for lengths and so on. So you could use that. It should be stable versus or against any kind of change of a scale. So the distribution must be such that if you change the scale, your list is multiplied every entry by any number, then different from 10, because in that case it repeats itself. In that case, the distribution must be the same. So it must be not stable, invariant the change of scales. And if the distribution were uniform, that's impossible, because imagine these are the digits I had before, and these are the digits I have after multiplying by 2. So all the numbers that started with by 1, after multiplying by 2, now will start with 2 or with 3. Not exactly the half-half, because that depends on the second digit that has its own law, and the third, and the fourth, and so on. But approximately, well, let's say half go to 2, half go to 3. So you have a certain frequency here. It's impossible to have the same frequency in 2 and the same frequency in 3, because this has to split. So if it is stable, if it is invariant, must be something different. So the sum of the frequency of 2 and 3 is the same as the frequency of 1. The same for 2, that goes to 4 and 5, 3 goes to 6, 7, 4 to 8 and 9, and now all the numbers, the list that started with 5, 6, 7, 8, or 9, then go to 1. So 1 is feeding from all of this. So if it is invariant, the frequency of this, the sum of them equals the frequency of 1. So it's clear that 1 must appear more frequently, and then 2, and then 3, and so on. And this is the key point. The distribution must be invariant. This is called the Newcomb-Benford law. In many cases, just Benford law, but it's more fair to mention Newcomb. I will talk about that a little later. This is the law. This is one of the few equations. So this is, we are not going to prove it. It's not difficult to prove it under the ansatz that the distribution is invariant. And this is strictly this, which is not exactly B, because when I created B, I added some noise. Or to all the distribution, I added some noise, just to mimic what one would expect in a real situation with a finite number of entries. But this is so, with 1, 2, and 3, you accumulate approximately 60%. Okay, let me put that. 60% of the numbers in the list start with 1, 2, and 3. The other 40 is left to the other number with decreasing frequency. Well, the names of Newcomb and Benford is interesting. This is Simon Newcomb. He was a Canadian. I think he was Canadian. And so, and what's happened is that when he visited the library to consult a table of logarithms to make calculations, he was struck by the fact that the pages that started with 1 were more worn than the other pages. So people, as I came today, many other people are coming every day. They are consulting the table for doing calculations. It's very curious. They are looking for numbers that start with 1 more frequently than with 2 or 3, etc., etc. And very curiously, Benford, about 50 years later, observed exactly the same without knowing that. This Newcomb published that in a 2-page paper as a curiosity. Benford made a much extensive and not only the mathematical demonstration, also with data. I will show you in a moment some of the table of the data he considered. So after that, the law was actually known by his name. But to do just this, also Newcomb had discovered that. There is a law according to which there is no law that is known after the name of the first person who discovered that. This is called the Stigler law. It's called the Stigler law because Stigler wrote a paper saying the Stigler law of eponymy. And he said, well, this law, I was not the first one who discovered. It was discovered a long time ago by other people. It's called the Stigler law as to confirm the law itself. He didn't discover the law, then the name has a different. So the same happens here. And why the table of logarithms? Here you have a photograph of my own table of logarithms, because I'm old enough to have to pass an exam of calculation using this table when I was in high school. No? When I was about 15 years old, you had to obtain that because there were no pocket calculators. And then when you had to solve a mathematical problem, you had to use the table of logarithms to pass the multiplication, take the logarithms, and then convert multiplication to summations, and then invert that. So that's why I didn't check whether the first pages of this table are more worn, because they were not very worn. Okay, because I was using that only at that time. Okay, so in his paper, Benford demonstrated the validity of the law in many situations like that. This is a table taken from his paper. So there are more than 20, the list includes 20,000 more entries and different, very different, even numbers appear in Reader Digest, even addresses, many crazy things. So he was very clever in doing that, very patient. And then on average, well, in each case there are deviations. The tendency is always there, of course. But there is a very, very good agreement when you take you combine all the numbers there, and there are small variations with respect to, okay? And I think because I'm sweating, this is sliding. Okay, okay. And well, I can show you also if this works, and I think it's not going to work unless I leave. Yeah, I have to. I don't know why this is. Okay. Well, this is the web page where you can change. Oh, sorry. For instance, this is Twitter users. I will take a loan amount. Okay. You can find variation because there are real numbers and maybe even the total number of entries is not very high, but anything. Population, Mexico. Okay, so there are some about 30%, then it is decaying, so more or less you have this kind of behavior. We already saw that. And there is an application that is, I wrote a popularization paper with a student for her bachelor thesis about that. So you have here the Benford distribution, which is the one, the orange one, and then these are for the population of cities in Badajoz, Cáceres, the whole province, the whole Spain. Then you will see some variation, but the tendency is there. The same with stellar distances in light year of parsec to the brightest stars. Also with the sunspots. Sunspots is very limited number, the number of sunspots per day. And of course, there are not 1 million of them, so it's more limited. But still, you have something similar. Also with the price of products in a supermarket. Here, there is an artificial manipulation by the manager, of the store that could change a little bit to, for instance, if something is going to cost 10 euros or 10,000 florins, then you write 9.9, something like that. So you are distorting a little bit. But in any case, you cannot avoid having this kind of tendency. And the application is for tax fraud. There is even books by some people about that. So when you fabricate, so be aware of that. So be careful. When you fabricate, not you, with someone else fabricates the tax revenue forms, if that person is not aware of that, maybe the inspector could see there are some deviations of the Benford law that are suspicious. That doesn't mean that you are a fraudster. But let's see in detail of that, because I'm not going to spend so much time in something that more or less is in agreement with the law. But here I'm going to spend some time because maybe something strange. Also, for election data, and if there is a fraud, maybe one could see some big deviations of that. Scientific data, and all of us have read about some fake data fabricated to increase your reputation as a scientist, and then you have to withdraw or retract and so on, quality control, risk management, etc. Okay, so maybe it's a little bit later than I expected, but let's go now to the Parrondo paradox. Parrondo was the guy who, as I said before, first informed me about the Benford law. Well, now it's a different thing. Now imagine you go to a casino with 2 rooms where you can play different games. In room A, the game you can play is just your roulette. You have a normal roulette, a standard roulette. And let's suppose that you are not going to bet individual numbers. You are going to bet on red. So this is quite usual. You bet $1, €1, 1,000 florins, whatever, to red number. If the roulette spins and you have a red, then you have one more unit. If not, you lose that, okay? And the probability of winning, there are 18 red numbers, but the total numbers are 70 because a part of the 18 black number, you have the 0. So the 0 is the advantage. You know that. I mean, everyone is aware of that. It's the advantage of the casino, the home, the house. So the probability, maybe even under those circumstances, you play because you want to have some fun and you don't care so much about losing, but you know that you are going to lose on average because the probability of winning is less than 50%. So the average loss per turn is easy to compute, is 2.70%. So if you play many times, every time you play, on average, you are losing that. Here you have the story of 50 individual players, or maybe you have been playing for 50 days in a row, and then one day maybe you were very lucky. You started from 0, 0 is the reference, so your capital could be 1,000,000, 100, whatever. At the end of the 5,000 turns, you win. Here also you win, but after that you are losing, and on average you are losing this percentage. So, of course, this is a losing game. If there were not 0, then the probability of winning will be 50%. The average will be 0, so this is a fair game. In that case, there are as many histories above as are below, and then the average is practically 0. Not exactly 0, because here there are only 50 histories, but this is expected. The average loss or average win is 0. But this is if there were no 0, but there is a 0, and then you have that. Okay, so enough for room A. Room B. Room B is a little bit more sophisticated. The rules are a little bit different, because in room B you have again a roulette, but also you have here a deck of Spanish cards. They are Spanish cards because I'm Spanish, and also because in that case, in the Spanish deck of cards, there are only 40 cards. Because there are normally there is no, you have 7, but there is no 8, 9, I think so, no? Yeah. From 7 you jump to this, we call that sota, so there is not 8, 9. In Ecuador, do you play the same? No, why not? Okay, you have that. And then either you play with this or that. That depends on your capital. If your capital is not a multiple of 3, then you are lucky. You have a capital of 100, which is not multiple of 3 or whatever. It's not a multiple of 3. Then, as before, you bet $1 to red, but you have 2 opportunities. So you don't have red at the first time. Okay, don't worry. Try again, only 2 times. And then the probability of winning is less than 35%, 75, less than 3/4, slightly less than 75% because of the 0, but it's much higher than 50%. This is not multiple of 3. However, if your capital at the moment happens, you are winning, now losing, if your capital is multiple of 3, then the game is different. You have to draw from the deck of cards, which are shuffle, of course. You draw a card, and you need to have 1 ace to win. So you have 1 probability of winning of 1/10, so 10%. So if your capital is not a multiple of 3, high probability of winning, because you have 2 opportunities. If not, it's a multiple of 3, then well, you have more probability of not drawing an ace than otherwise. Would you play that game? Well, one could say, yeah, I could say, I'm going to do a simple calculation. On average, one could say 1/3 of the time, my capital will be multiple of 3. 2/3 of the time will not be multiple of 3. So 2/3 of the time, I have this probability of winning. 1/3, I have only 10%, but the combination gives me more than 50%. So one could say, okay, that's a good, this time I'm going to beat the casino. Well, this is not true. This is not true because what happens by the own nature of the game, of course I'm not showing the calculations, the fraction of times your capital is multiple of 3 is more than 1/3. It's 38%. And then the combination gives you something not very below 50, but below 50. In fact, when you make simulations, this is the result. It's the same. You have the slope gives you the probability of losing per turn. Before we have 2.70%. You have now less than that. But on average, maybe not this day, maybe not that day, but on average, you play many, all of us create an association to play and then share the winnings, the society will collapse because in the end we will be losing, okay? So very, very, one can prove that more or less analytically. If there were not 0, the probability of the capital being a multiple of 3 will be slightly higher than before. Before you have that, now you have this. But because there is no 0, when your capital is not a multiple of 3, the probability of winning is 75%. So you have practically the same frequency of multiples of 3, even which is a little worse than before, but it is compensated, and in that case, the average loss is 0. And these are a real simulation with how many? 50? I think 50 games. Okay, so, but again, we have the 0. So in summary, in room A, we have a good time. Maybe we are drinking. The atmosphere is very glamorous. But on average, we are losing. Here also we are losing. And in both cases, because of the presence of the 0, otherwise everything will be fair. Okay? And now the owner of the casino gives you, okay, I'm going to give you a fair opportunity. Imagine that I offer you the possibility of toss a coin, even you or myself, I toss a coin. If the outcome is head, for instance, then you play A. If it is odd, then you play B. So you change from A to B. When you play A, it doesn't matter whether your capital is multiple of 3 or not. It could be or not, but that doesn't affect the rules. When by accident you have to play in room B, of course, at that moment, you know that either you take a card or you have to ask the casino to spin the roulette, depending on whether your capital is not or is a multiple of 3. So you are offered that. What would be your answer? So again, you will need to vote in the second. So there are 4 possibilities now. You say, no, 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 no. Because my average will be the mean value. I have in A, I have 2.70. Here I have that, so I will be having the average of that. So no, that is enough. Or you can say, well, no, because both losses are going to accumulate and I will have even more. Or you can say, no, yes, yes, okay, I think this time I can win. So thank you, yeah, I'll try that. Or none of the above, of course. Always there is a possibility of that none of those answers are correct. Now it's your time for you to, okay? What do you think that is? So do you have the, no, it's the same, it's the same. Let me, maybe I have to, you don't need to read the QR again, because now I think you can see the second slide. When I say that one of them is correct, it means that not from the psychological point of view. For instance, this guy, this I expect to win. This is not very mathematically well expressed, but I mean, you understand what I mean. And none of the above is that because it's fair, or, I mean, anything that is not included in the previous three options. Okay, let's see what happens. I already see that 5 people thought A1, B1, C1, D5. Do you need to see that, or? Okay, no, because I know that so most of the people think that it's none of the above. And the other possibility that is, okay, I'm going to vote, but not using that. I'm going to vote with this, and my choice will be C. Okay, I'm going to win. I'll show you that. Yeah, I have to. This white, yellow line is the result of the simulations. All of these are simulations, but these can be obtained analytically by doing calculations. It's a Markov chain. What we have is a kind of Markov chain, so it can be solved with the tools of mathematical physics and statistical physics and so on. But in any case, you have a win of, I will show that, about, if I remember well, I don't remember right now. I will show the, well, one can see here. You have won about 30 euros or dollars after 5,000 trials, so you can obtain the slope. That's giving you the average win per time, but you are winning. And you see other curves which correspond to other possibilities. This is the 50-50. But if you play 30% of the times A and 70 B, you even win a little more. And with 60, even more. But however, with 40, you are practically fair. With 30, 20, 10, you are losing. With 90, so there is an interval, which is, you can see, this is the analytical result. These are not simulation results. So this is the average win. You have, in most of the cases, losses, negative wins. But in this interval, you have win. 50 is there. This is better, about 60 or so. Okay, so you win, you alternate with a frequency of between approximately 40% of the times B, 60% of the times A, and the other limit is 87% times B, and then 13% A. But these are the streams. These are similar to this 90 and to this 40. 87 will be there, more or less. And the optimal choice will be 65, okay? In that case, your win is not a very big win, but it's a win. So here, if you play only game A, you have a loss of 2.7. You play only game B, you have a loss of 1.2, something like that. If you combine, you could have something better than that, even positive, and this is what you have. What's the reason? Is that when you alternate, the frequency of your capital being a multiple of 3 decays and you play more game A. So game A is helping you to have a frequency of multiples of 3, which are the cases you play the bad. You have to draw an ace. So as you play more A, then the fraction of times your capital multiple of 3 goes from 38% to 33. Here is 1/3. But that doesn't mean that you mean B here, because only if you play B, you will make the cases where your capital is not a multiple of 3 to benefit you. So you need not to play very much, very frequently game B, but enough times to have the opportunity to recover your losses, because from time to time, when your capital is not multiple of 3, okay, I have 2 opportunities and then I recover. So that only happens in this interval. It's the same interval I was showing that. So there are 2 competing effects, okay? And as a result of that competing effect, winning, losing and losing can combine to give a winning. And other possibilities that instead of changing from A to B at random with a given probability, you do that systematically. So in that case, one has to do that mainly by trial and error. So with a combination A, B, B, so 3 times in a row game room A, then 2 times room B, then 3 times room A, and so on and so on. That, in that case, you have a win similar to the maximum you will have in the case of random changes. It's a random alternation. And you can do that better with this. This is a very strange. You have A, 4 Bs, A, 4 Bs, A, 4 Bs. In that case, you get a very, very good. In other combination, you lose. Okay? Just to being near the end, this is Parrondo, who will be 60, maybe he's already 60, but when he proposed that, he was 32 only, and he did that, he's a statistical physicist, and he was interested in Brownian ratchets. Brownian ratchets are motors that work at the microscopic level thanks to Brownian motion, things like that. I'm not going to delve very much into that. This is an image taken from that. And he was interested in a particular kind of Brownian ratchet that is called the flashing ratchet. And he was interested in the physics of that. And he obtained a kind of paradoxical effect. And when trying to explain that in a conference, I think it was in Italy, he was to illustrate that. He did a parallel an analogy with the game. And someone in the audience became impressed by that and wrote a paper called The Parrondo Game and so on. He didn't write the paper, so it was an Australian guy. And then, well, he became more or less famous because of that. Not famous as Mbappé, who is going to play with Real Madrid, but relatively famous. What is a flashing ratchet? Why the analogy? Imagine this is game A, this is game B. Game A, you have a potential. You can imagine that forces the particle on average to move from right to left. This is the 0. If there were no 0, that would be horizontal. But because of that, this particle diffused, right, they move at random, right and left, but with more probability to left. So in the end, they move from right to left. This is game B. In game B, also, you have the same kind of random motion. In that case, you have this kind of ratchet, but also because of the tilt, particle diffuse on average from right to left. Now, you alternate. So you have B, and now you switch off this potential and have that. What happens is that particle diffuse, and when you, again, switch on this potential, some particle, although on average they are moving from left to right, some particle have moved sufficiently to the right of that so that they are favored to go here. while these one are practically at the same position, because those which are here, they didn't escape. They go again as that. So if you compare the first and the third, you realize that on average, particles are moving from left to right. So this is the analogy with the game. Of course, you cannot alternate between B and A with any frequency you want. You need to have enough time A, so that particles have time to diffuse and all of that. Well, the main general conclusion is that individual losing strategies can lead to winning strategies when they are alternative, when they are combined and have been applied for game theory, finance, in biology, statistical physics, quantum physics, information theory, engineering control systems. If you go to Clarivate, Web of Science, and look for papers with the topic Parrondo, possibly you will find 300 papers or something like that. And I think this is, here I'm not going to click that. This is a page, a blog where someone is showing many crazy applications one is curious about. So that, I think this is the end. So the take-home messages in general is that these are two examples that challenge our intuition, especially when probability and randomness is involved. And well, seemingly simple rules can lead to surprising results. You need to be skeptical. I mean, don't trust too much your intuition. You must trust it, but be careful with that. And we must be open to have counterintuitive possibilities. And then this is a provocative test that maybe you can think on your own experience, daily life, or some paradoxical or counterintuitive results that are surrounding you. So that's all what I wanted to say. So thank you for your attention. Now, if you have questions, I will be happy.
Thank you very much, Andrés, for this nice presentation. Before the questions, I would like to ask something for the audience. How many of you heard about this Benford law before this talk? Please hands you up. Okay, and how many of you heard something about this Parrondo's paradox before this talk?
No one of you.
Nobody. Okay.
So I'm happy.
Interesting. Okay.
Not the names.
But you knew the.
Not the names.
Okay. So the questions, please. If you
Yeah. The games are really dangerous from the casino's point of view. Like, if it's random, yes, on average you would accept it. But if you offer the chance that if your money is not divisible by 3, then you have 2/3 of chance of winning, a lot of people would start to play, okay, I go in with my money, not like that, have a good chance of winning. If I win, I go out. If I don't win, I bet again. And then you have a chance of getting an edge above the casino. Okay, the casino wouldn't let you play like that if they are sane, but by changing the initial conditions, you could mess with the casino.
Changing the initial condition.
Yes.
You mean that your initial capital is not a multiple of 3, for instance, in room B, so that you can start?
Yes.
Okay, but yeah, I mean the fair, so don't, yeah, the casino will tell you, if I were, okay, you choose game B, you compromise to play at least 20 times. Yeah. Of course, everything is artificial.
Yes. And for the first one, I was wondering if it's somewhat because it is not random. Like, we have a 10-digit number structure, so if you go over, then the first digits are much more likely. So if you have a different digit, like 12-digit number system, again, the first number will be much more likely, because if you go over one category, that will become more frequent because it's not necessarily infinite. So for a random distribution, like really random, if, for example, dice throws, okay, let's say a 10-sided die, which is random, and if it throws 0, we throw again. If it doesn't show real random distribution, probably we should have a talk with the manufacturer, and the people will start to use the dice for something interesting.
Well, according to the Benford law, is not verified. You fabricate, the numbers are random. As I said, the lottery numbers, for instance, they don't obey that because they don't need to do that, of course, because they are randomly chosen, 1 from 9, including 0 at random. There is no need to expect that it would be invariant under change of scale. It's very paradoxical that in some cases the Benford law works even when it is not so clear that this should be invariant. For instance, in the case of population. Population, you have so many people. The only way I see of having invariance is that you can count the population of a city by counting individuals, or maybe by counting number of arms. Suppose all of them have 2 arms. So what you are doing is multiplying by 2. Or maybe I count by pairs. How many pairs? Not necessarily couples of, but how many pairs? How you have here 1 pair, 2 pair? I mean, this is the equivalent to invariance. But if it is truly random or quasi-random, there might be. And another before you.
The number might be somewhat random, but the system is not.
The system is not, yeah.
The way we are calculating.
For instance, I can create very easily, and I have done that, a long list of numbers obtained at random with the Benford distribution.
Yeah, but you
so
look at the first digit. Did you look at the last digit?
The last depends, I mean, the Benford law extends to the second digit, to the third digit, to the fourth digit. What happened? The second digit, and so on, 0 appears. What is the second digit more frequent? What would you think? Would be the between 0 and 9, what is the more frequent second digit? 0. 0. 0. Then 1, so you have again the same, but it's a smoothing out. For the third digit, it's even smoother. So you go, imagine you have a list of numbers with 10 digits, and you go to the last one, will be practically uniform. Case A. So the differences are smoothing out and so on. Another generalization is to a base different from 10. You have number in base in hexadecimal. You will have, instead of having log in base 10, you have log in base 16 or in whatever, and you have exactly the same law.
Yeah, I would expect that kind of. I'm not really sure about the binary, but for the rest, I would expect that.
Yeah, for the binary it would be too trivial because the first digit is 1 according to that, and the second will be. Yeah. But of course, you can apply the formula yet, but that
is, I think, because of how we count. How we count, like the numbers, like the differences are disappearing because we are getting to larger and larger numbers, so it's more likely that...
what happens is that, I mean, to derive the law, the end what you have, the log of the number have a uniform distribution. And then when you take how many numbers do I have between this value and that value, then you make the integral, and then you can have that. And as a result, the second digit, because you have the probability for combination of, you have, what is the probability of having 1, 0, probability of having 1, 1, probability of having 1, 2, 1, 3, until 9, 9. So you have, I don't know how many, because 0, 1, about 80 possibilities for pairs. And then the probability of the second digit being 0 is the sum of 1, 0, 2, 0, 3, 0, and as a result, when you sum all of them, the differences are not so big. So 0 is more, the sum of 1, 0, 2, 0 is more probable than the sum of 1, 9, 2, 9, 3, 9, and so on. But they are not so big difference. And as you go farther and farther and farther, the differences tend to become level, to be the same. So I mean, mathematically, it is very well defined. One can try that. And empirically, you can try to do that. I haven't done that for the second digit in the samples I showed, but it should work. I think in the paper I was mentioning we had a table for the first digit, the second digit, maybe the third digit. Just a table to know this is what happens.
May I understand correctly that you mentioned that, for example, the lottery numbers doesn't follow this Newton-Benford law of the first significant digit. But what is the condition? The condition is that the distribution function should be wide enough in logarithmic scale. It should be almost constant in a logarithmic scale. And this is basically the.
No, but I mean, in logarithmic scale, the uniformity is equivalent to the Benford law, mathematically speaking. Okay. Now you need, of course, statistically, you need a big list to have that more or less close to the theory. But when can you anticipate that the law should apply? Even not rigorously, because there could be some other influences. For me, the answer is when I can imagine that if you have units, I mean, if those numbers are accompanied by units, artificial units in some cases, so that there is no way to expect that the distribution is going to change if you multiply everything by a factor. You can think of many examples where...
If this factor is very, very large, you will lose this behavior.
If it's very large, what?
This factor, if you multiply...
No. The only thing is that if the factor is 10 or 100, then you are not changing anything. But if the factor is 2 or 2 point, in the paper you sent me, the factor was 1.1 or something like that. They check that. So you multiply by 11, which is 1.1, or you multiply by 12, or by 2, or by 5, then the Benford law doesn't change statistically. I mean, now some numbers started with a given digit, now they start with a different digit. But this is compensated by the fact that, and so on and so on. So statistically, the distribution is the same. Not precise way you have 1,000 numbers. There could be some fluctuation, but imagine you have an infinite number. Benford, one of the things that were in the list was a square root of n. He was talking a square root of 1, 2, 3, 4. So the square root of the first 100 natural numbers. Again, the first digit followed the law very, very closely. I don't know exactly why, because in that case, why there is invariance under change of scale, I'm not sure. But in that case, it happened with the square root, with some other kind of manipulation, mathematical manipulation. And even the number of streets were the addresses of people. He was taking the addresses of many people. I don't know how he got that. He tells the story in the paper. And by analyzing the first digit of the, the American system, the address is a long number. No, it's because it also takes into account the intersection between avenues and streets and so on, which are numbered, I suppose. And then by paying attention to the first digit of the address, again, he obtained that. Is that invariant? Should be invariant? I don't see why, but it works. But in the case it is invariant, by sure.